Hello. Now we will do the parallel combination for capacitor. So if there are two capacitors which are connected in parallel, we want to calculate the effective capacitance in place of this. So this is my two capacitors which are connected in parallel, and as you know, the parallel combination means the two capacitors, the each and every end of the capacitor is connected to the other side. So this end is connected to this side and this end is connected to this side. Okay, so this is your parallel combination, and I want to replace this combination with this one, C effective. But in both the cases, the voltage across the whole assembly as well as the total charge passing through the whole assembly should remain constant if the system is to remain same. Okay, so we want to calculate C effective in this case. So let's say I'm saying this A and B voltage will be voltage difference will be VA minus VB here as well and on both the sides. So in this case, the voltage across both the capacitors in case of parallel combination will remain same. So since voltage will remain same, charges will be different obviously. So I'm assuming from A, plus Q charge is moving. So plus Q will come out here because the charge cannot be destroyed. The same charge will be moving here as well. So here as well, plus Q charge will move and the plus Q charge will come here. So positive Q charge will be onto this plate and minus Q charge will be onto the other plate. But in this case, if you see, the plus Q charge which is moving, it is encountering a joint. And at the joint, this charge will get redistributed. So out of this plus Q, let's say, plus Q1 is moving on to the other side. So minus Q1 will be here. So from this side, plus Q1 will come on to the remaining charge will go on to the other side because the charge cannot be destroyed. So here, onto this side, plus of Q minus Q1 charge will be there, and here we'll have minus of Q minus Q1, and this charge will move on to this side. So Q1 and plus this charge, if you add these two charges, ultimately the plus Q will move to the B point. Okay. Now, this A point you see, from this A point to this point, ultimately there is no resistance, there is no capacitor. So whatever is the potential at this point, it will be same here, and whatever is the potential at this point, it will be remain same. And this point and this point. Okay, so let's talk about these 2 points, this one A dash and B dash, which is similar to the A and B. So VA minus VB will be equals to VA dash minus VB dash, and that will be similar to VA double dash, which is this point, and this is B double dash minus VB double dash. So this VA dash minus VB dash, let's calculate. Let's calculate the potential between these 2 points. So potential between these 2 points will be equals to charge onto the capacitor divided by capacitance. So it will be Q1 upon C1, and as we know, this VA dash minus VB dash is nothing but VA minus VB. Or we can say this Q1 is equals to C1 VA minus VB. This is my equation 1. Okay, now let's go for this C2 capacitor. For the C2 capacitor, the VA double dash, I'll calculate the potential. I'll calculate the potential difference across the C2 capacitor, which is VA double dash minus VB double dash, which is nothing but VA minus VB, and the value will be Q minus Q1 upon C2. Or this will become Q minus Q1 is equals to C2 times of VA minus VB. This is equation 2. Now if I add both of these equations, upon addition 1 plus 2. If I add these two, so on to the left hand side, if you see, it is Q minus Q1 and here it is Q1. So if we add Q1 with Q minus Q1, you will be having Q, and that will be equals to C1 plus C2. I'll be taking VA minus VB common, so VA minus VB. This is equation 3. Okay, this is the net equation. So this is the equation between the net charge passing through the A point, and that is in corresponding to the VA minus VB. Now let's come back to the effective circuit. This is my effective net circuit, which I am replacing by from parallel combination. So for effective circuit. So for effective circuit, if I calculate the potential difference across its corner, which is VA minus VB, because it should not change, that will be equals to charge upon capacitance, which I have defined as C effective, or we can say the charge will be equals to C effective multiplied with VA minus VB, and that is the equation 4. Now see, if both of these circuits are similar circuits, then their formulas should be same. Now if you compare between the equation 3 and 4, the Q left hand side is same, and onto the right hand side if you see the VA minus VB here as well and VA minus VB here as well. So the rest of the thing, which is C effective and in this case C1 plus C2, it should also be same, because if these two circuits are similar circuit, their equation should also be same. So upon comparison, between 3 and 4 will have C effective is equals to C1 plus C2. So if I'm having a parallel combination, then the effective capacitance of that parallel combination will be the addition of their individual capacitances. Okay, so this is for two capacitors. If two capacitors are in parallel combination, what if n number of capacitors are in parallel combination? Like if I make the diagram, it's like that. If n number of capacitors are joined in parallel, C1, C2, C3, and this is Cn. And if I want to replace this whole circuit, parallel combination circuit, by a single capacitance of C effective, then this C effective will be equals to C1 plus C2 up to Cn. You just add all these capacitance. So this is the formula. One should memorize this formula. So if in any problem we will encounter a combination of capacitor, which is a parallel combination, we will be replacing that parallel combination using this formula by a single capacitor. And in that case, after that, we can further simplify the circuit and we can find whatever is being asked in the question. Okay, so this is your parallel combination, the formula for parallel combination. Thank you.